Hello and welcome. This is quite a complicated problem, an actual Brayton cycle with reheat and regeneration. So let's see what are the information supplied. The inlet conditions given to us, the volume flow rate is given to us. So state 1 is completely known. The compressor has a compression ratio of 12. That means this has an overall pressure ratio of 12, which might be distributed between these two turbines. Turbine 1 has a pressure ratio of 3, so automatically the other one will have a pressure ratio of 4. Notice that the compressor also has a isentropic efficiency of all compressors and turbines are 90%. That's why we have double states at the exit. One is isentropic, one is actual. So to save time, what I'm going to do, I will essentially start from test code, regenerate the solution, and go over the solution step by step. Basically, I'm going to reverse engineer the solution in this case to reduce the video time. Okay, so we must follow the open specific branch, vapor power and gas power. And this is about PG model. We click PG model, and here comes the page, and I'll pick up the test code, which is right here. So this is our problem. So the test code should be here, and I'm going to just Control A, Control C. So instead of starting from scratch, I'm starting from the solution. But okay, so now let's start as if we are starting from scratch. Let's see how we would proceed if we started from a blank test step. Of course, we first evaluate all the states. State 1 is our inlet state, and as you can see, pressure is supplied, temperature is supplied, and volume flow rate is supplied. State 1 is fully calculated. Okay, so now let's go to state 2. Recall state 2 is the isentropic. State 2 is the isentropic state at the exit of the compressor. So we'll go back and forth between the power, the schematic, and the calculation. So what we see here is that pressure is given in terms of pressure ratio, and entropy is also must be equal. And just one. Where is pressure ratio defined? Obviously, in the I/O panel. Let's just see the user panel, user codes. You can see that the pressure ratio, as well as all the other, the high pressure turbine ratio is 3, pressure ratio is 12, maximum temperature, reheat temperature, temperature after reheat, and the compressor and two turbine efficiencies. They're all equal, but we can easily make them different. And finally, the efficiency of the regenerator. These are all variables, parameters of the problem. So state 3, recall, is the compressor exit state, the actual compressor exit state. Again, for that, the pressure is the same as P2 or P1 times P ratio. And enthalpy, in this case, is found from, actually, it is found from the efficiency definition. So you can see that it's divided by eta C. So H3 is found from the compressor efficiency, and the expression is substituted. If you put the mouse over such an expression, the formula should appear here on the second help panel on the top. So you can see that if I put the mouse over, then you can see that the H3 equals H1 plus H2 minus H1 divided by eta C, the efficiency of the compressor that connects our actual exit state with the isentropic exit state. Okay, state 4 is the state right after the regenerator. Again, pressure is the same, and the temperature T4 is obtained by the definition of regeneration efficiency. Again, the formula is shown on top, so you could type that in. And by the way, mass flow rate is always same amongst all these states, so I'm not repeating that everywhere. m dot is equals m dot 1. All right, so let's go. What is state 5? State 5 is the turbine inlet state. Just let me remind you again. State 5, notice, is right after the combustor, so it will have the maximum temperature, and the pressure doesn't change here, so pressure will be same as pressure at 2. So as you can see, for state 5, the pressure is same as pressure at 2, and turbine inlet temperature is the maximum temperatures. So state 6 is the exit of the high pressure turbine, the first turbine. So as you can see, the pressure at the exit has to be obtained differently, P2 divided by high pressure turbine ratio, P ratio of HP, which is 3. It's isentropic to state 5, so therefore state 6 is obtained. State 7 will be similarly the actual exit pressure of the turbine, high pressure turbine. So again, P7 is same as P6, and enthalpy at the exit is obtained from the definition of turbine efficiency. State 8 is our reheat state, so the pressure doesn't change, pressure is same as before, the previous state, and the temperature of reheat is given, which is, therefore this state 8 can be completely calculated. For state 9, again, this is also, state 8 is also the inlet to the turbine, second turbine, so state 9 is the isentropic exit state. At state 9, we have already reached the ambient pressure P1, and entropy is equal to state 8. Let's go back to the schematic to make sure we are correct. See, state 9 is the exit to the turbine 2, and it's the isentropic turbine state 9, and the pressure would be at state 9 would be the same as pressure at 1, since there is no pressure loss in the regenerator or any heat exchangers. Then state 10 is going to be obviously our actual exit state. So it's again, we are taking advantage of the definition of turbine efficiency here. So pressure and enthalpy are known for state 10. And finally, state 11. State 11 is our state after the regenerator of the exhaust gas. So it's obtained from an energy balance. Enthalpy is obtained from an energy balance on the regenerator. Basically, we know that if you look at the regenerator, the heat loss from state 10 to 11, H10 minus H11 will be the proportional to the heat loss, and heat gain will be what? H4 minus H3. So they must be equal, allowing us to find H11. And that's exactly what we have done here. Therefore, state 11 is known, and that completes all the calculations of all different states. So it's a good idea to take a look at the TS diagram. As you can imagine, what we expect is what we get, 1, 2, then we go. So this is essentially the complex TS diagram that we have been developing. Okay, so now that everything makes sense, we go to the device analysis panel and load. Device 1 is our turbine, between 1 and 3, as you can see, turbine work is found. For device 2, we make sure inlet is, this is device 2 here is, sorry, the device 1 is the compressor, that's why the work is negative. And device 2, I believe, is the turbine, 4 to 5. No, sorry, device 2 is 4 to 5 is the combustor. So 1 to 3 is the actual compressor. So we are dealing with the actual compressor, actual turbine, etc. So let's go back and start from scratch. Device 1 is 1 to 3 is the actual compressor. That's why work is negative. Device 2 is the combustor, 4 to 5, and only heat transfer is positive. Device 3 is the first turbine, 5 to 7. Again, work is shown. Device 4 is our reheat combustor, 7 to 8. So there should be some heat transfer as shown here. And device 5 is our low pressure turbine between 8 and 10. And as you can see, work is produced. Let's go and check. This is 8 to 10. So this is our low pressure turbine, 8 to 10. And then finally the regenerator will be a multi-flow device, but we want to make sure if work is 0, then heat transfer must be 0 if we have done the calculation correctly. So this is our device 6, which is the regenerator. As you can see, from gas is heated from state 3 to state 4, 3 to 4, whereas it is cooled down from 10, it loses heat from 10 to 11. So when we solve the problem using W dot external equals 0, Q dot is found to be 0, 2. So that shows, and finally, the final heat exchanger, which takes us back to the inlet state, state 11 to state 1, produces the heat loss in the final heat exchanger. And that completes the cycle. There is no other device left. And if you go to the cycle panel, all the desired variables, such as the thermal efficiency, W dot net, which must be equal to Q dot net, are found. To do a parametric study, it's quite simple. We can just go to the I/O panel, and suppose there was no regenerator in this problem, so we could just say, you know what, the regenerator efficiency is 0. We register the change and do a super calculate, and that's it. We come back to the cycle panel, notice the thermal efficiency has been drastically reduced because there is no regenerator. Okay, I don't want to make the video any longer than it needs to be, and you understand that you could start from scratch. It would take probably 30 minutes to build up the problem, but because the test code is there, you can pretty quickly jumpstart a solution.